This video is the first part in an attempt to understand the Dreamer4 model, which achieves the state-of-the-art performance on several reinforcement learning benchmarks. I'll start with a very brief recap of the original Dreamer idea. Then we will go to this paper. So in original Dreamer, which was introduced way back, at a high level, Dreamer is a model-based reinforcement learning algorithm that learns a lateral dynamic model and then uses imagination to generate a policy that model can implement on the environment. So it learns latent representation using environment data and then uses a reward model to get rewards, and then uses the policy learned in imagination rollout and then trains itself. So everything happens in imagination. So Dreamer4 takes this whole idea and then introduces some key changes. So we will start with the background part here. So in Dreamer4, everything starts with how latent representation is modeled. So for that to understand, we have to understand flow matching. And to understand flow matching, we have to understand diffusion models. So I will show how diffusion model works. Then we will go to the flow matching. First, we will go to the diffusion model. In diffusion model, we have this noise, this Gaussian distribution, and here we have image distribution. So in a nutshell, in diffusion model, image has some Gaussian noise introduced to it, and then model learns how much noise is added and then removes that noise to get the original image. That's the whole idea of diffusion model. So let's say here we have image with some noise. So it learns to go from here, this image, this is in between. So it is a mixture of image and noise, and it learns to go from here to here. So it learns a mapping from this distribution, that is Gaussian distribution, to go to the image distribution. So this is the whole simplified example and explanation of diffusion model. So we will take this idea into our flow model. So in flow model, we have this same Gaussian distribution, and here we have same image distribution. But in flow model, instead of trying to predict the noise, it tries to predict the velocity at any given point. So let's say our data is here right now. And it tries to learn how to go from here in this xt to this x1. And xt is modeled using both x0 and x1. So in paper, it is given as xt is modeled using both x0, this is Gaussian noise, and this is our original image. So let's put the value of t as this tau, but I will just read it as t. So let's just put t as 0. So we will get here 0, and this 1 multiplied with x0 will just get this pure noise, and this will just become 0. So at 0, t is equal to 0, we have this pure noise. At t is equal to 1, when we put t is equal to 1, it just becomes whole image, and you can see that x0 is sampled from Gaussian and x1 is sampled from image. So this is just t going from 0 to 1, and this is our xt, and we saw the example of how xt is calculated. So xt can be in middle, so let's say if it was 0.5, so it will be in middle, and it learns from going from here to here. Model learns how to go from this point to this image distribution. So how does the model do that? It does that by understanding the velocity vector, velocity field. So why velocity? Because it has to have a direction, right? So if it went to this direction, it will not work because it goes to the Gaussian noise. So it has to learn the direction also, and how much magnitude it should go into that direction. It can't just skyrocket and go to other distribution. So it has to learn both magnitude also and direction also, and also the speed at which it goes. So this whole thing gives us a velocity. And how do we calculate velocity in our physics? So we know from physics we have dx by dt is equal to v. Same it applies here, because this xt is just a position here. So we can just use a differentiation, and we can just differentiate it to get this value. This is just simple differentiation. So we got this x1 minus x0. The same thing is used here. So this is our true velocity, and this is what our model will predict. And we used L2, that is MSE, mean squared error, to as a loss, to calculate the loss. This was the whole point of this this section till here, and this one is just for the inference part. This part is just for the inference part that will come out later. And I'll just go through this again to just give whole overview. So first, model samples x0, this pure image, and we get xt using this formula, and then model get this true velocity from this x0 at x1, and then learns how to get to that velocity using the parameters and using that loss. And we can see in our model that xt is used inside the model with the time parameter. This was the explanation of this flow mechanism, and in the next video we will see how the inference part comes. How inference part uses Euler's ODE solver, and then we will also see this in code, like this whole thing we will see in the code and how everything works. And just briefly show the output, so we will have some motivation. So we can see it was able to learn the distribution from the MNIST dataset. This is MNIST dataset. It is not so clear because I have used simple architecture, but we can see it was still able to learn using flow matching this whole distribution. You can see this is 2, this is 4, this looks like 1. So this works. So thank you for watching this video.